All right, this is the Advanced Placement Chemistry assignment for day 40. It's Basic Gas Laws on Monday, October the 21st. Problem 1. 20 newtons of force is applied to a 4 square meter area. What pressure is applied to the area? So your force is 20 newtons, and the area is 4 square meters. So your formula for pressure, it's how much force is applied to a given unit of area. So it's force over area. That's going to be 20 newtons over 4, which equals 5. And a newton per meter squared is called a pascal. So 5 pascals of pressure. Next is the same question essentially, except we reduce the area. So 20 newtons over 2 meters squared. That's going to give you 10 pascals. So the third question asks, how does reducing the area affect the pressure? Well, clearly you can increase the pressure by increasing the amount of force on the area. But you can also increase the pressure by decreasing the amount of area that force is being applied to. So that the answer is reducing the area increases the pressure. Okay, and that's the simple point of that exercise. Okay, now we're going to do some real simple conversions. You may have done some of these in 8th grade science. We're going to convert centigrade to Kelvin. The centigrade scale is one that is based around the properties of water. So 0 degrees centigrade is the freezing point of water, and 100 degrees centigrade is defined as the boiling point of water. So what they then did is they said, okay, we got 0, we got 100, so we're simply going to define a degree as 1/100th of the distance between the freezing point of water and the boiling point of water, and that's a degree on the centigrade scale. It happens also to be a degree on the Kelvin scale. So the Kelvin scale uses the same unit of measure of degree change, or what a degree is, as the centigrade scale. The only difference between the two, and it's significant, is what they define as being 0 degrees. Centigrade has a very practical definition, the freezing point of water. That's 0 degrees. But scientists said we need a scale where 0 really means 0. It means there's nothing lower than that number. There's no negative numbers on the Kelvin scale. It's the lowest possible temperature you could have in the universe. It's when you've taken all the energy out of an electron, or out of an atom rather, so its electrons just collapse in on it, then that's at 0 energy. And so that's the definition of 0 on the Kelvin scale. It's the lowest possible temperature that you can have. So to get between the two, to get to Kelvin, you take the centigrade reading or the centigrade number and add 273 to it. So for 0 degrees, it's 0 plus 273 equals 273. And you don't say degrees Kelvin, you just say kelvins. It's just the convention. 20 degrees, so it's 20 plus 273. And that's going to be 293 Kelvin. 253 plus 273. And that's going to be 526. For negative, you just subtract. And that's going to be 75 Kelvin. Okay, that's that. Now we'll go in the other direction. The formula is just the opposite. C equals K minus 273. So we got 0K minus 273. So the lowest possible temperature as expressed on the centigrade scale is negative 273 degrees centigrade. .373 minus 273 is 100 degrees centigrade. So that's the boiling point of water. going to give you a negative 20 degrees centigrade. (25). This is a temperature you'll come across in a lot of chemistry problems. 25 degrees centigrade. Okay, that's a 159. So we can read that. Okay, that's it. Very basic, simple conversions, but you will do these a lot in gas laws. All right, now we never use Fahrenheit in chemistry. It's the scale used here in the United States when you watch the weather and they give you temperatures there in Fahrenheit. But let's just do a couple just to be sure you know the conversion. So to convert to Fahrenheit from centigrade, the formula is Fahrenheit is 9/5. Sometimes you'll see it 1.8. It's the same thing. Times the centigrade temperature plus 32. Okay, so 9/5 times 20 plus 32. So on a calculator, it would be 20 times 9 divided by 5 plus 32. And that's going to give you 68 degrees Fahrenheit. Okay, negative 32 is going to be 9/5. Negative 32 plus 32. And that's going to give you negative 41.7. Okay. All right, next we go centigrade. We go to centigrade from Fahrenheit. So the formula, if you just do the algebra on this and solve for C, you'll get this. It's going to be 5/9, then a parenthesis, Fahrenheit minus 32. Okay, and if you run that number, you will get, for 85 degrees Fahrenheit, you'll get 29.4 degrees centigrade. And for negative 43, you'll get negative 41.7 degrees centigrade. All right, keep going. Describe the function of a barometer. A barometer, it measures atmospheric pressure, like the pressure of the air around us. Okay, and there you go. Now we're going to go on to the next page. All right, so there's a whole variety in your notes of measures of pressure. What I'm going to do is up above, and go ahead and do this also, is write them out, just so you get used to seeing them over and over again and understand them. So at sea level, which is where we are, 1 atmosphere, we are at, it is 1 atmosphere at sea level. That's basically the definition of 1 atmosphere. That's equal in pascals to, we're going to use 101,000. Actually, a more precise number is 101.9, but we're going to go ahead and use this. That's pascals. Now, more commonly, instead of using pascals, because 100,000 is kind of a big number, they just call it 101 kilopascals. That's thousands of pascals. Now that's equal to 760 millimeters of mercury. What that means is, in a barometer, the atmospheric pressure at sea level will push a column of mercury up a tube, basically 3/4 of a meter, 760 millimeters. And that's how that number came about. And since they decided that, that was kind of a unit of measure that a lot of people, I guess, didn't want to write, they just decided to give it a new name. They call it a torr. But you still see millimeters of mercury. So there are 5 different units for pressure, and you're going to see all of them in your problems. So you want to get used to making these conversions. They're very basic, so I'm going to go through them fairly quickly. Okay, the first one. We're trying to get to torr. We start with 3.5 atmospheres. And now you can turn any one combination of these 5 into a conversion factor. We need atmospheres to cancel. We need to end up with torr on the top. So we're going to put 760 torr over 1 atmosphere. Cancel atmospheres. And go ahead and multiply. And you will get 2,660 torr. Okay, next one. We're trying to get to pascals. And we're going to start with 2.1 atmospheres. So we need a conversion between atmospheres and pascals. So there it is right there, these two. We need atmospheres to cancel out. So it's 101,000 pascals for every 1 atmosphere. Cancel, cancel. And what you end up with there is 212,100 pascals. Next up, we're trying to go for kilopascals, starting with atmospheres. So our conversion is going to be right here. Need atmospheres to cancel out. Kilopascals to end up on top. It's 101 kilopascals for every 1 atmosphere. And you crunch the numbers on that, and you get 545.4 kilopascals. Okay, next up we want to get to atmospheres. Again, whatever you're looking for, put way over on the left, or on the right rather. What you're starting with, you put way over on the left. Again, our conversion is going to be kilopascals to atmosphere right here. Kilopascals on the bottom. And 1 atmosphere on the top. And when you do that, you get 1.33 atmospheres. Next up, we're trying to get to atmospheres again. From 798 millimeters of mercury. Okay, we need millimeters of mercury. We need that on the bottom to cancel. We got atmospheres on the top. And when you run that, you get 1.05. Finally, we want torr as a final answer. We're going to start with 98.7 kilopascals. Okay, the conversion is, there's torr, there's kilopascals. So we need kilopascals on the bottom. So 101 kPa on the bottom and 760 torr on the top. And you run the numbers on that and you end up with 742.7 torr. And that's the answer to that. Okay, let's keep going. What are the 4 variables that affect the behavior of gases? So these are really the only things you have to think about when you're dealing with gases. The first one is number of moles. That's how many particles do you have in that container. That's going to have an effect on the behavior of the gas. And it's expressed in moles, and they use N to express moles. So that's number of moles. So it's not grams, okay? If they give you grams, you got to convert to moles just like you always do. If they give you liters, well, that's what we're going to talk about here. Because the next one is volume, and that's usually in liters. The next one is pressure, and that can be in just pressure. That can be in any of those units we just talked about. So it could be in a variety of different units of measure. But pressure, and you can think of that very simply as how often do those atoms or molecules hit the side of the container. And next one is temperature. It's kind of obvious, and that's going to put energy into these gas particles. By the way, we use the word particles to mean atoms or molecules. It's just whatever the gas is. And this is going to determine how fast they move. The temperature is going to put energy into them. It's going to determine how fast they move. So number of moles, volume, pressure, and temperature. And temperature should always be converted into Kelvin. All right. Number 12. Number 12 is an interesting problem. I threw it in there. I used to give it to advanced physics classes. I threw it in there for you just as a practice, just a challenge problem. We're going to do it in class tomorrow. But since you're not a physics class, there's some things in here that you might not know. So let me give those to you. So I gave you one conversion here. Let's read the problem. A set of bookshelves rests on a hard floor surface on 4 legs. That's significant. Each having a cross-sectional dimension of 3 times 4.1 centimeters. So whatever that area is of that leg, you got to multiply it by 4 because you have 4 legs. And they're in contact with the floor. The total mass of the shelves plus the books on the stack is 262 kilograms. So your mass equals 262 kilograms, rather, kg. So calculate the pressure in pascals. First of all, let's identify, just like we did with molarity, we broke it down into moles per liter, or molality, we broke it down into moles per kilogram of solvent. What is a pascal? So a pascal, a unit of measure pascal, is a newton of force, that's force, over meter squared, and that's area. Okay. So how do we get to newtons of force? We're given kilograms. So there's a formula, force equals mass, and that's what you have right here, times acceleration. But what's the acceleration? Well, it's the acceleration pulling down on the bookcase, which we also, so that force is called the weight. And so the acceleration we use is the acceleration due to gravity, and that's 9.81 meters per second squared. So when you set up your problem way over here on the left, you want to end up with newtons on the top. You're trying to go for pascals over meters squared on the bottom. So you're starting with some combination of centimeters here. You want to end up with meters squared. You're starting with kilograms. You have this formula here along with the A equals gravitational acceleration. So you need to end up with some number of newtons of force, because this is what's in newtons, is the force. And see if you can figure that one out. Okay, we'll do that as a challenge problem, and we'll do that tomorrow in class. All right, let's go ahead and move on. So now we're going to use some of the 3 basic gas laws and just practice them a little bit. Pretty simple. This is basic chemistry stuff. So let's go ahead and start number 13. So the pressure in an 8.7 liter container is 24.2 atmospheres. The volume is then increased to 10.3 liters. What is the new pressure and which law applies? So it's a pressure volume problem, and that would be Boyle's law. Let's go ahead and write these down. So Boyle's law is this. You do not have to memorize whose law is whose, but you do have to know how to write them. So Boyle's law is that the pressure before, that's what we mean by 1, times the volume before equals the pressure after, that's what we mean by 2, times the volume after. So that's a pressure volume problem, and that's Boyle's law. The next one is Charles' law, and that is the volume before over the temperature before equals the volume after over the temperature after. And finally is Gay-Lussac's law, and that's going to be the pressure before over the temperature before equals the pressure after over the temperature after. Again, you don't need to identify these by name, but I'll just give you the way I remember it. You think of your own mnemonic. Boil. When you think of boiling water, what do you think of? You think of temperature. Boyle's law is the one that doesn't have temperature in it. Okay, Charles. I used to have a roommate in college named Charles. He liked to watch a lot of TV. So Charles is the one with TV in it. You think of your own that would make sense to you. And Gay-Lussac. Well, Gay-Lussac is a French name, and I think of the French and Indian Wars, and Plains Indians used to live in tents called teepees. So Gay-Lussac has teepee in it. Again, you think of your own. Sometimes the weirder they are, the better they're easier they are to remember. Okay, so this one is going to be a Boyle's law. And I'd like you to always write out a formula, even though it's on a piece of paper in front of you, possibly. Write it out anyway. So for this problem, P1 V1 equals P2 V2. And what you can then do is just write the numbers down below. So the initial pressure is 24.2 atmospheres. I know that it's asking me for a new pressure, so it's going to be in atmospheres. So I'm not going to bother with the units of measure here. It's 8.7 liters. And that equals P2. That's what I'm trying to find. And the new volume is 10.3 liters. Okay, and you do the math on that, and you end up with your new pressure is going to be 20.4 atmospheres. So stop. Before you just walk away from this problem after crunching the numbers, think about what you're saying here. You're saying that if your volume goes up from 8.7 to 10.3 liters, it gets bigger. That means the particles inside, the gas particles, are not going to hit the sides as often because they have to travel farther to get from one side of the container to the other. That's going to reduce the pressure. And since the volume went up by, it looks like about 25% by 8.7 to 10.3, that means the pressure is going to go down by about 25%. So 24 down to 20, roughly 25%. So think about intuitively what's going on with the gas particles as this all happens. Okay, the next problem, number 14. The temperature in a 9.3 liter expandable container, got a bug on my paper here, is 23 degrees centigrade. If the temperature is increased to 68 degrees centigrade, what is the new volume? Think about what you think would happen, just intuitively. If you increase the temperature of those gas molecules inside that container, an expandable container means it can get bigger. So think of a balloon. What would happen? What would happen to the size of that container if you increased the energy inside of those gas molecules? All right, so which law applies? So this is a temperature and a volume, so it's a TV, so that's a Charles law. Okay, now anytime you've got temperature and gas laws, you've got to convert to Kelvin. So let's go ahead and do that. So we start out with 273 plus our initial temperature, which is 23. That's going to give us 296 Kelvin. Then 273 plus our final temperature is 68. Okay, and that's going to get us to 341 Kelvin. All right, so let's go ahead and plug the numbers in. Let's write the formula first. So it's the TV1. So it's volume 1 over temperature 1 equals volume 2, that's the after, over temperature 2, that's the after. So let's plug in the numbers. The V1 is 9.3 over T1 is don't use 23, use 296, equals, we want to find out the new volume, that's V2, what we're looking for, and that's over 341. Okay. And volume I know is going to be in liters, so the volume 2 is going to turn out to be 10.7 liters. Again, let's intuitively think about this. We increased our temperature by about over here. we increased our temperature. The point I want to make, I'm going to make the point second. We increased our temperature by, it looks like about 10 to 15%, probably closer to 15%, going from here to here. But if you look at these two temperatures, we increased it by 3 times. So if you use these numbers, you're going to get a totally wrong answer. So you've got to be sure to make this conversion. But we increased the temperature once we converted to Kelvin by about 15%. So what that means is we've increased the volume by about 10 to 15%. Okay, right there between these two numbers. So if you increase the energy by increasing the temperature, you increase the energy in those molecules, then you're going to increase the volume. That's going to expand your balloon. Okay, let's go on to the next one. The pressure in a 98.6 liter container is 97 kilopascals. What will the pressure be if the volume is reduced to 67.1 liters? So think about that. Pressure is how often the gas particles hit the sides. If you reduce the volume, you squeeze down that balloon so that the volume is much smaller. If they're going the same speed as they were before, which they are, they're going to hit a lot more often. That means they're going to hit with a lot more pressure. So you can expect your pressure to go up if you decrease your volume. So this is a pressure volume question, PV. So again, we're going back to Boyle's law. And let's go ahead and write it. P1 V1 equals P2 V2. And plug in your numbers. When you write the formula, you just put the numbers right down below. So this is going to be 97 kilopascals times 98.6 liters. And then we're trying to find the new pressure, P2. And the new volume, the second volume, is 67.1. So our pressure ends up being, when you run the numbers, do the algebra on that, 67. Okay, so we'll do the math here. So it's 97 times 98.6 divided by 67.1. And that's going to give you 142.5. And the units we were using in this problem are kilopascal. Alright, so what happened? We squeezed down the volume from 98 down to 67, and that made our pressure go up from 97 to 142. Because at a smaller volume, the molecules moving at a particular speed are going to start hitting the walls more often inside of that smaller room. Alright, next up, let's go to 16. And we have, if the pressure in a 1.2 liter flexible container is increased from 67 degrees to 98 degrees centigrade, what will be the new volume? It should actually say temperature, so you can check that and make that. Okay, so we're going to change that word pressure to temperature. Alright, so first we got to convert the temperatures from centigrade to Kelvin. Come over here and do that. 273 plus 67. And that's going to give you 340 Kelvin. 273 plus 98. That's going to give you 371 Kelvin. Alright. So now, which law applies? This is a temperature and volume. Because it's a flexible container, the volume is going to increase. So that's a TV, so that's Charles. So it's V1 over T1 equals V2 over T2. We plug in the numbers there. So our initial volume is 1.2 liters. Our initial temperature is 340 Kelvin. Okay, our final volume is what we're looking for, V2. And our final temperature is 371 Kelvin. So when you run the numbers on that, you will end up with a volume of 1.31 liters. So let's think about what's happening. We're increasing the temperature. That means we're putting more energy into the gas particles. So they're going to speed up. So if that container's flexible, they're going to start hitting those sides faster and harder. They're going to cause that balloon to expand. So you multiply the temperature by, it looks like about 10% from 340 up to 371. So that means your volume increased by about 10% from 1.2 to 1.3. So about 10% roughly, okay? So that makes sense. All right, next one. If the pressure in a container is 1.3 atmosphere and the temperature is 51 degrees centigrade, what will the new temperature be if the pressure is reduced to 0.94 atmospheres? Which law applies? So this is a pressure and a temperature, so it's a PT or TP, so that's Gay-Lussac. And that relationship is P1 over T1 equals P2 over T2. Again, you don't have to know that that was Gay-Lussac's, but you do need to know this relationship from memory. Okay, so let's go ahead. So the P1 is 1.3. The T1 is, now we got temperature, we got to convert. 273 plus 51. And that's going to equal 324. Degrees. And the new temperature is what we're trying to find out. So that's going to be 1.3 is the pressure over 324, which equals the pressure after is 0.94. And that's going to be over our T2. That's what we're trying to find is the temperature. All right, and if you go ahead and run the numbers on that, you get temperature T2 equals 234.2 Kelvin. Now it's possible the problem might ask you to convert back to centigrade. You would just subtract 273 from that, and that would give you your centigrade answer. So again, let's think about it intuitively, what's going on. The pressure dropped. So that means the molecules are not moving, hitting the sides as fast. They're not hitting with as much energy. So it went down by, it looks like about 50, about a third, it looks like. So that means the temperature ought to go up. The temperature ought to go down by about the same, by about a third. So from 324 to 234, it's about a third. Okay, so that's your answer there. And finally, combined gas laws, that was an error. Those shouldn't have been put on there. I haven't edited those problems, so you can skip those. Those are going to be on tomorrow's assignment. And that's it. That takes care of that. So we'll work on a new assignment. You can finish this one up in class. And hope you have a good evening.